Module 3, the target of test. In this module, we will cover different types of manufacturing defects that can arise in electronic devices. We will identify that these faults are abstract defects, and then define the two main categories of fault models: static, stuck-at, fault model, and dynamic, transition, fault model. Finally, we'll discuss pattern faults and how they can impact the performance of electronic devices. Defects are errors or glitches or mistakes in the manufacturing process that produce a chip that does not behave exactly the way it is expected to. Defects are presumed to cause incorrect behavior later if not immediately, and therefore must be rejected. For example, in the picture on the left, there is some extra metal shorting two metal traces. In the picture on the right, a metal trace has become detached from the substrate and buckled. If the buckled trace is not touching the other trace, there may not be a functional error, but do you want to ship it? Will later mechanical vibration cause it to either short to its neighbor, or might it break off and create an open? There is damage in a line across a number of traces, so there is more going on here than that simplistic analysis would suggest. While we would like to directly test for each and every possible defect, there is in fact no way to directly observe most of them. So we observe their effect on circuit operation and categorize those behaviors. So, while it is impossible to know, a priori, all of the possible defects that could occur on a chip, much less observe, then we can observe the specific incorrect behavior that would be caused by the defects. We call these observable behaviors faults, and the set of such behaviors we test for, a fault model. The most commonly used fault model is the stuck-at model we have just illustrated. Based on many years of use, it does a very good job of detecting defects that cause static, non-time varying, incorrect behavior. This would include hard shorts and opens in the various metal traces, for instance. In recent years, newer technologies have been exhibiting time-varying behavior due to defects, and these behaviors are described by the transition fault model, which observes when a pin is too slow when it changes state. This will occur when a short or open is resistive rather than hard, for instance. Tests commonly used in technology nodes above 16 nanometer that observe analog behaviors include the IDDQ test that observes supply current changes while stuck faults are stimulated, and I/O parametric tests that observe whether the I/O drivers and receivers meet their analog current and voltage specifications. In smaller geometries, 16 nanometer and less, it is becoming more common to test for faults inside the standard cell models themselves. One common model is called cell-aware. For instance, let's pretend that the short in the picture is shorting the transistor gate metal, red in the drawing of a 2-transistor inverter, to the power supply ground trace, the cyan trans across the bottom. The transistor gates are the input of the inverter, so this defect would cause the input of the inverter to be stuck at ground, or 0, and the output to be stuck at 1. This stuck-at behavior can be observed digitally, using the circuits of the chip itself. Thus, rather than testing directly for defects, a short in this case, we test for the observable digital, and sometimes analog, behavior that the defects cause. In this manner, many different kinds of defects which cannot be directly observed are abstracted into a smaller set of behaviors that can be directly observed. As mentioned earlier, the most common fault model, by far, is the stuck-at fault model. This has been in use since the early 1970s, and has proven very effective at detecting most manufacturing defects that affect static logic operations. In this model, it is assumed that a defect will cause the pin of a gate to behave as if it is stuck at a specific logic value, 0, 1, and sometimes X. The defect could, in fact, be in the transistor itself or on the traces connecting to the gate. The stuck-at fault model is also referred to as static faults, because the behavior does not vary with time. These days, most companies are pushing to achieve 99% stuck-at fault coverage. These stuck-at faults models can correlate to typical shorts and open, among other things. Stuck-at 0 fault observe when input or any pin is stuck permanently with ground. Stuck-at 1 fault observe when input or any pin is stuck permanently with VDD. For example, in this diagram of an inverter, we assume that, due to a manufacturing process problem, not all of the metal shown in red is etched away properly, leaving an excess of metal at the bottom of the shape. That would be the transistor gate. This excess of metal overlays the location of the via from the ground power distribution trace to the drain of the transistor. So the gate will be shorted to ground when the via is etched and filled. This excess metal is the defect. Its fault behavior is the gate input, stuck at 0, or, equivalently, the gate output, stuck at 1, for the static logic tests. Note that the short may also create other abnormal behaviors. In IDDQ testing, an attempt to drive the input to this inverter high will cause excess current. There may be other abnormal behaviors in other test modes. A fault model that has been around for a while, but is coming into greater use as we move to smaller and smaller transistor dimensions, is the transition fault model. In this model, defects such as resistive shorts and opens are abstracted to their behavior. The signal toggles, but does so too slowly. The faults are called slow to rise and slow to fall faults, and sometimes collectively referred to as dynamic faults, since the behavior is time varying. Obviously, to test for these faults behaviors, a transition must be generated that propagates through the pin that the fault is defined for. In the sense that a stuck at value is just an extreme of a slow to change value, this fault model is a superset of the stuck at fault model. For example, in this inverter layout diagram, again, a process problem has prevented the via from the input of the red gate level metal from being properly filled. Some metal was deposited, but the via exhibits many ohms of resistance, instead of its nominal fraction of an ohm. Since the gates of the two transistors have a significant amount of capacitance, the RC time constant of the input is now much slower than expected, and the signal will not toggle with its expected transition time. It could easily be a couple of orders of magnitude slower than the expected transition time, and will prevent the chip from operating in its functional mode. Here are some examples of defects that cause transition fault behavior. First, in the upper photograph, you can see that there is an apparent gap in one of the horizontal traces, yet this passes static tests. When the chip is sliced through the gap, shown in the lower photograph, we can see that there is a thin conductive layer that creates a resistive open. The defect causes the input driven by this net to exhibit a slow transition, but not very slow. Here is another example. You can see a faint streak across the face of the chip. This is some form of contamination of the silicon, and it creates a resistive short across several nodes. Again, the part passes static tests. This additional load on the nets causes a slow transition at one or more inputs. These two examples came from a discussion of difficult to detect defects. Most defects that cause transition fault behavior will be worse than these two examples. For more content and learnings, visit Cadence support site. To enroll for the courses, visit www.cadence.com. Click on the Support tab and open the Digital Design and Sign-Off Training section to enroll for the courses. Click on the Digital Design and Sign-Off Training section. Choose the course from the respective technologies and enroll for the course. Click on Enroll icon to enroll for the respective course. Thank you.